Hello students, in this video we'll discuss the Cornu spiral and curves that have the prescribed curvature. Let's first consider the curve. Consider gamma of t, which is going to be a planar curve, the integral from 0 to t of cosine of s squared over 2 ds, then the integral from 0 to t of sine of s squared over 2 ds. This is known as the Cornu spiral, or Euler spiral. And these Cornu spirals look something like this. If you were to plot them using software, you'll see that they have the following sort of structure. Like that. Like something like that. Those are Cornu spirals. And we want to put the curve into arc length parameter, right? So let's compute the derivative. So the derivative of this thing, we use the fundamental theorem of calculus, is going to be what? By the fundamental theorem of calculus, this is going to be cosine of t squared over 2, and then sine of t squared over 2, like that. And so what's the speed of this curve, right? So in other words, the length of this curve, gamma prime of t, is equal to square root of cosine squared of t squared over 2 plus sine squared of t squared over 2, right? And of course, that's just equal to 1, right? In other words, we have a unit speed curve. So this is a unit speed curve. In other words, this is really gamma of s. So this is really gamma of t is really gamma of s, where s is the arc length parameter. S is the arc length parameter. So our curve is already an arc length parameter, which is beautiful, because now I can compute. So now that tells me that d gamma dt, so t hat of s, is just what we have over here, right? It's just cosine of s squared over 2, and then sine of s squared over like that. Excellent. Now let's compute the unit normal vector, right? So it's the principal normal vector. So if I do d by dt, dt ds, we know by Ferney's array, this is going to be the curvature of s times p hat of s. Okay, that's Ferney's array number 1. And so let's compute what dt ds is, right? So what is dt ds? So dt ds is going to be what? Is going to be negative, and then s sine of s squared over 2, and then what? And then a positive cosine, so s cosine of s squared over 2, like this, right? And so, of course, the curvature is just the norm of this thing over here. So in other words, what can we say? This implies it's the curvature of this curve is going to be. So the curvature, kappa of s, is just the length of this vector over here, right? Is going to be the square root of s squared sine squared s over 2 plus s squared cosine squared of s over 2. Cosine squared of s squared over 2, like this. And there's an s squared over there, right? So, okay, and so this simplifies just to what? Just to s. So in other words, this curve exhibits linear growth and curvature, right? So this is a linear growth and curvature. What we see from this figure over here, we have no, like, essentially straight curvature over here. And as we move along, I mean, tighter and tighter and tighter and tighter circles, right? So the radius of oscillation is increasing over there, right? Excellent. And of course, since this is a planar curve, we know that the torsion is equal to 0 too. So trivially, the torsion is equal to 0 because it's a planar curve, right? So I have a curve whose curvature is s, its torsion is 0, right? So the linear growth and curvature. Now I can actually modify this procedure, right? So given curvature k of s, any curvature you want, let's say t of s is going to be the integral from some fixed s0 to s of this function over here, k of u du. And if I put this over here, an antiderivative of this curvature, we can use a modified version over here. So let's look at this gamma 1 of t, 1, which is going to be the arrow from 0 to t. And then I'm going to put a cosine of this function over here. So I'm going to put a cosine of t of s ds. And then the integral from 0 to t of the sine of t of s ds, right? Now, the exact same calculation shows me what? Shows me that when I do gamma prime, I'm going to have cosine of what? I'm going to have a cosine of t, sine of t of t. So that's going to be a unit speed curve, so this is a unit speed curve. And when I do the second derivative, the derivative of t is going to come out, right? So in other words, this will tell me that the curvature of this gamma 1 of s, because it's really a function of t, is going to be the derivative is d by ds of t of s. Of course, what's d by ds of t of s? That should be k of s, right? So k of s. So if you want to prescribe a particular curvature to a curve, so if I give you a scalar function and you want to find a curve whose curvature is given by that scalar function, you can always find a planar curve with a prescribed curvature by this sort of generalization of this idea with the Cornu spiral, right? So in other words, I can basically tinker with this formula over here. And of course, now these integrals over here might not be computable. Like these things over here are called Fermat integrals, right? And the Fermat integrals are very important in optics, which we'll discuss in further videos. But the key feature is here that I want to prescribe a curvature, I can use this planar curve to prescribe any curvature I wish. Thank you very much.